Hi there, Mr. Newland again. So I want to talk about what happens when you've got conductors and insulators uh, near each other, surrounding each other, and what implications that might have for Gauss's law and the E field. So first, I want to point out this scenario here. Imagine we've got a slab of metal and we are able to look at it from the side such that if you put this piece of metal, this metal plate, into an E field that already exists, somebody's made an E field, maybe they have a giant capacitor, and you slide this metal plate into that region, the E field that the metal encounters is going to cause electrons to want to move this way. So electrons end up moving. They're evenly distributed. Wait, I should have said this before. This metal plate has no charge on it beforehand, so it's no net charge. And then you put it in the E field, and the electrons are going to be induced to move around. Remember, electrons in a conductor are essentially free to move along the surface. Okay, well, what that leaves on the side opposite where the electrons moved is a net positive charge. And you'll notice it matches up as the E field through this thing. So from over here to this point, you go this direction, we're seeing the electrons are moving that way, and if there were any protons or positive charges, they would move that way. And so the net charge on the plate is like you see here. But if you were to actually investigate this region down inside of it, the electrons in this area here, they're not free to move. Okay? So what we really did is the overall surface of the thing, electrons are moving around, and there's a net negative charge on that side and a net positive charge on that side, but the inside of this thing is neutral. So for conductors, for a conductor that is put into an E field, if it was neutrally charged before, no electrons are coming from out of these regions over here on the left and the right, so there's no net change of electrons. So that means that overall, even though this side is induced to have a negative charge and this side is induced to have a positive charge, the center part of this thing has no net change. It's still not charged at all. So whenever you mix conductors together, you have to think about it from that perspective. Okay, so we could apply Gauss's law and think about on this side it was sigma over epsilon naught, and on that side it was sigma over epsilon naught, and that the near field is sigma over 2 epsilon naught. We could remember that, but that actually isn't where I wanted to go with this video. I wanted to so remember, if you put a non-charged conductor into an E field, you'll end up with an induced charge on it, negative on one side, positive on the other side, aligning with the E field, but the region inside the slab of metal actually doesn't have any charge at all. So if we move over to this example, we've got a metal sphere that is surrounding a charged insulating sphere. And the reason that matters, this orange guy right here is going to end up having a charge distributed all the way through. It is not a conductor. So starting down in the middle, there's a little bit of charge, a little bit more here, a little bit more here, and it's evenly distributed through this thing. I had a previous video where I showed you what the E field would be if you were to draw a Gaussian surface inside, not a conductor, but an insulating sphere. And I also showed you a video where I drew a Gaussian surface outside a charged conducting sphere and what that E field would be. And we're going to combine those two ideas with what it means to put a conductor near something like this. So if this whole thing has a positive charge Q, that means the E field is everywhere radially outward from it, meaning just like we had in this scenario here, we're going to have to end up, as a matter of fact, before I say that, let's think about drawing a Gaussian surface out here. Let's draw a Gaussian surface way out here. I don't know what happened there. Guys, that was crazy. Let's erase it, because I can. And so I'll just try to draw it like that. That's terrible. So imagine that purple thing is a Gaussian surface. What I'm saying now is I can assume that all of the charge, by the way, this metal sphere that I surrounded the positive charge Q with, it didn't have a charge on it beforehand. There's going to be an induced charge on it. Well, how would that look from the outside? If this purple thing represented a Gaussian surface farther away, then the net charge, so remember, the flux, the electric flux, is the Q enclosed over epsilon naught. Well, the metal sphere had no charge on it when I brought it into this scenario. So from outside, the charge is still only from this thing down inside. So the charge is actually Q over epsilon naught. So that's actually a really good starting point for analyzing what's going on in the conductor. That means if the inside of this orange guy, if that entire, not the inside of it, if the orange sphere is the net charge on it is Q, remembering that it's evenly distributed throughout its entire volume. But if the charge on this thing is Q, then a Gaussian surface drawn out here needs to see the same thing. So that means the outside of this sphere must have a net charge of positive Q. But this metal shell, it's not a sphere, this metal shell is a conductor, which means that down inside there's no net charge. And if the outside has a plus Q, that means the inside must be a negative Q. Think about the weird implications there. So again, we had a charged orange sphere that's not a conductor, it's an insulator. And then we surrounded it by this metal shell that is a conductor, but it wasn't charged. What that does is it induces a charge on the sphere, on the shell, for a little while. Now, the way in this like hypothetical situation, I don't have any wires connecting anything. So assuming that the net charge on this little orange guy will never change, the net charge that's induced on the shell, never going to change. You would have to actually connect things together into a circuit to move some electrons around. So think about what's going on. This guy is a plus Q, meaning that the inner part of the conductor, which wasn't charged before, all of the electrons that are free to move near the surface are now going to bunch up here. So you end up with a net negative charge on the inside and a net positive charge on the outside. And the Gauss's law idea still works. If we draw a Gaussian sphere around the entire thing, the net charge is still Q, so Q over epsilon naught is the flux. So the reason this is so weird, so let's talk about these various points. There's point 1 down inside, there's point 2 that's in between the two, point 3 inside the conductor, and point 4. Well, let's do 1 first. I'm not going to go through the entire proof again, or the derivation, because there's another video that does just that, but we know what that is. In E field at point 1, we know the radius of our Gaussian surface is less than the radius of the sphere, which is called A, lowercase a in this case. So our Gaussian surface is less than A, so down in here somewhere. We already showed this in another video, was K times Q enclosed, times Q, over A cubed times R. So the E field for a Gaussian surface inside the orange guy, remembering this is not a conductor, but an insulator, it actually had to do with how much of the volume you've enclosed, which is why you got this ratio of R over A cubed. Okay? So that's the E field for a Gaussian surface inside the orange ball. KQ over A cubed times R. Okay? So let's do the second scenario. E2. So E2 is this Gaussian surface where the radius is greater than, so R greater than A. But it's also, it's also less than B, which is the distance from the center of the orange sphere to the inner shell. So that's a weird way to write it. Here, let's flip that. Let's make it look more like what I started with. So R is greater than A, but it's less than B. In that scenario, we've got a Gaussian surface that surrounds a charge Q, and we've already done this too. I've already shown you what that is. E2 is then just K times Q over R squared. It acts like a point charge, all of the charge centered at the middle there. So the E field for the Gaussian surface drawn inside the insulating sphere is KQ over K times Q over A cubed times R. If the Gaussian surface is outside the orange sphere but still inside our conductor, it acts like a point charge, KQ over R squared. Now let's talk about point 3. This one's really key because it has some pretty strange implications for things like a Faraday cage and how you get electricity to move over things and through things and things like that. Since this guy is a conductor, what we see is that there's a negative charge on the inside of the sphere, the shell, and a positive charge on the outside of the shell, but the inside has no charge. If there's no charge, there's no E field. So if we're greater than B, but less than A, wow. In this region, no, that's wrong. I just drew that wrong, guys, sorry. Let me try that again. So we've got C here, which is from the center of the orange guy out to the outer part of our shell, and B, which is the center of the orange guy to the inner part of the shell. So the distance between C and B is that area. So I wrote that wrong. Apologies. So what I mean is that E equals, I'm not going to tell you what it is yet, for R greater than B but less than C. So inside the shell. We know what that is actually. It's 0. There's no enclosed net charge in this region. Now, the closer you get to the surface, there are quantum mechanical effects. If this were a semiconductor, the rules would be different. But for purposes of just theoretically or hypothetically, qualitatively analyzing what's going on, there's no charge in this region marked with the 3. There's a net negative on this side, a net positive on that side, no charge on the inside, and no electrons were brought in. So the shell wasn't charged when we brought it into this region where there's an E field, meaning that there's a field induced on it instead. I'm sorry, a charge induced on it instead. The net charge is still 0, but the inside is negative, the outside is positive, and the E field at 0.3 is then 0. Okay, and then for one that I think is kind of, this one has a lot of implications for what Gauss's law can tell us about more complicated systems like gravity. So now at point 4, we're going to draw a Gaussian surface, kind of like my terrible, that's the worst Gaussian sphere ever, since it's not a sphere. But at area 4, we're saying that R is greater than C. So we're now outside the shell. So now the Gaussian surface is out here. Well, we actually already talked about this. And we know what this guy is. At that particular scenario, it's kind of like having K times Q over R squared. And so look, the E field here was KQ over R squared. The E field here is KQ over R squared. So if you're surrounding the orange ball, but you're outside, you're inside the shell, there's an E field based on how far away you are. If you're way out here, it's exact same scenario. So the deal is, the shell ends up masking what's going on the inside, in a sense. We know there's a charge Q down inside the shell, but we don't know what's going on. From the outside, if all you can see is the outside, the shell says, I have a plus Q on the outside of my surface. So exactly what's going on is not terribly clear without being able to analyze the thing a little bit further. But that's how Gauss's law works for a conductor that's surrounding a charged whatever. Remember, this guy's an insulator, this guy's a conductor. All right, that's good enough for now.